Hi, this is John Bush, and this is lecture 9 of a lecture series on the Miocene aquifer system in Moscow and Pullman. Because of some technical difficulties, the sign says I'm Pamela Dunlap. That's my wife, who's helped along with Steve when putting all these talks together. I assume you'll remember that I'm not Pam, I'm John. This lecture was going to be on the geologic controls of water level decline and model testing. Those that have been following along know that we have finished talking about the upper aquifer, and then we did a model on the lower aquifer. This is going to follow a little bit differently. Just going to check a couple of things, do some thinking within the model. We'll do some model testing on 3 areas, which I think were the most important keys of our model. And then we'll talk about potential geologic controls on water level decline and look a little bit into the future, or think a little bit into the future. So for those who haven't followed along, there were sort of 3 key areas on talking about the Moscow aquifer system, Moscow Pullman aquifer system, the Moscow mountain slopes, sort of the sink, what I call the sink at Albion, which is controlling, in my opinion, controlling groundwater movement, and then the barrier zone out to the west of Pullman. So we're going to think a little bit within the model. I call it model testing. It's really just thinking to see whether things make sense on a double check. And then we'll come back and talk about water level decline. And only one slide to remind us of from the past lectures. This is that slide looking from Kamiak Butte, looking east towards Moscow Mountain. And remember that our system, our Miocene aquifer system, underlies the loess fields. Basically, it's not really flat, but I sometimes call it the flat area or the low elevation area. The end of the basalts, as we recall, they were flowed in over Pullman and flowed towards Moscow Mountain, is about where the cursor is now. They're relatively the change in slope. And we call this area at higher elevations gradually rising up to the tree line as being sort of the Moscow slopes. And the tree line is what I would refer to as a Moscow Mountain area. So just keeping those 3 in mind, what we're going to talk about first is this slope area. I think you should recall that it was mapped wrong by myself and some others, and decades of people thinking it was pretty much all granite, and all granite with a thin overlayer of loess, which is being farmed. The new data, starting with George Grader and some of my interpretations, show that this area is really underlain by a lot of sediments, weathered granite, and some granite highs, but not a solid granite area. And this is the area, the Moscow Mountain slopes, is where research has shown that there's recharge getting down into the system and then moving over to Pullman. So we're going to look at some thinking about that. And also I'll be pointing out that I think even up into the tree area, some area we haven't investigated much, I think recharge is getting into the subsurface even at higher elevations than we previously thought. The only way I could maybe test the model, because we decided, or I decided, that it was deposition by alluvial fans and braided streams, was to go back and review, just glance at the past literature. And I realized I hadn't spent enough time looking at some work done by Othberg and Breckenridge in 2002. They made a superficial map. They took my bedrock map and mapped subdivided the superficial units, the units on top, into different depositional entities, different types of deposits. And a tough area to map because it's mostly farm, very few road cuts, but using some road cuts and some areas where they dug ditches, they produced a map which shows some significant deposits, which helps, I think, support the model of more sediments in the subsurface than we had previously thought. One of the things that our Moscow model depended on, our Moscow Miocene model, depended on was the presence of debris flows. As you might recall, George Grader identified some of these from deposits at pretty high elevation. I postulated that those debris flows must be getting on out into the subsurface and even getting joining some of the basalt flows and going over the top of the basalt flows. Well, Othberg and Breckenridge mapped some debris flows that are quaternary in age, meaning somewhere in the last million years, but primarily probably in the last 100,000 years, mapped some of the debris flow deposits way out onto the flats over the basalt, some of them extending beyond the basalt edge. And that's really important to my thinking and helps sort of verify the model. If we had debris flows with the present topography in the last 100,000 years, we probably had debris flows, and the likely interpretation for back in the Miocene, where the topography was much steeper as the basalt flows filled up the basin. In the Miocene, when they were deposited, it was a lot wetter. It did not have the snowpack. The present day debris flows mapped by Othberg and Breckenridge may be owe their origin to extreme saturation from melting of snow. But it proves that debris flows could go a long ways away from the mountain front. And I felt like that helped verify the model that we used. Now, another thing that they talked about that they had discovered, they called hard saprolites. They discovered several saprolite horizons. Saprolites is a weathered soil, very thick clays generally. The saprolites they talked about are ones that had a lot of quartz granules, quartz cobbles, quartz sand, surrounded by clay. The interesting part about those saprolites that they talked about is downward, they would get so hard or as hard as rock. So you might ask, well, why was that important to understanding the Moscow mountain slopes? One of the problems I had interpreting the drill logs was a lot of the drillers would talk about soft granite, hard granite, alternating hard and soft, 10-foot units, 20-foot units, 5-foot units. And it always bothered me, what were they talking about? Because it's difficult, conceptual-wise, to have hard granite overlying soft granite. So, but I ignored that. I couldn't figure it out. It was clear that in some cases, I thought, well, the hard granite wasn't really granite. Or some kind of lithified material, and then the soft granite was the fact that sediments or weathered granite exist. Well, if you think about these hard saprolites, and you think about the number of times that the area was subjected to base level changes, remember 25 different flows coming over Pullman, each time one of those flows stopped, with the high rainfall, the humid climate, we've developed the saprolite. So I believe that in the future, something might help somebody out realizing that those, what they're reporting as saprolites, are equal to the alternating hard zones identified in many of the drill logs. And to me, it helps verify that I believe our interpretation of many depositional cycles in alluvial fans and braided streams is correct. Another thing that Othberg and Breckenridge noted, way up until the top of the rim, way up in the Moscow Mountain area, they noticed a lot of quaternary material, soft deposits, gravel, sand, soil, that if you looked at the right places and saw some exposures or saw some landslide scars, you would see that they're oftentimes overlain by soft weathered granites. So it points out that once again, there are lots more weathered granites, probably in the subsurface, than we had previously decided. For those who don't remember, the problem with detecting the sediments from granites, from weathered granites, is that the material coming up at the drill site is ground up material, and it's simply consisting of primarily of quartz and clay. And professionals and drillers alike for decades have identified that as granite in almost every one of the well holes. And the point is that this helps verify the map that they did and the work that they did helps verify that the subsurface is not granite, that many of the so-called granite wells are really alternation of sediments, saprolites, and weathered granites. And it would helps to verify that there are more areas of potential recharge sites all along the slopes, but also up into the mountain highs. Another area that was crucial, I picked out 3 things to think about with the model. Picked out the Moscow Mountain slopes, and I thought, well, the barrier zone is something that's important to the model. So I re-looked at the barrier zone. Now, for those that have forgotten, the barrier zone is somewhere starts in Pullman and out into the Union Flat Creek area. I believe, and some other people also follow up that thinking by believing that this area, that the basalts that can carry the lower aquifer water have poorly developed intraflow zones or something's out there, dikes, igneous dikes that are known to exist in that area. Something is slowing the water down, slowing the groundwater movement to the west. And one of the problems has been there's no deep production wells out there. We do have observation wells, but no deep production wells. And so they've been taking most numerical models and most thinkers, take the attributes, the hydrological attributes determined from Pullman and Moscow area where we have lots of wells, lots of tests, and applying them to this barrier area or the entire area on Union Flat Creek. It's my thinking that those areas have lower hydrological parameters. And what I mean is something like hydraulic conductivity. We know that the very high numbers come out of the Pullman-Moscow area. I suspect if we really could get some data that they're going to be much lower out here in this zone. Starts somewhere in Pullman and extends on out into the Union Flat Creek area, that the salts out here will not produce as much water from any individual well that they do back in the Moscow-Pullman area. And even though they are connected, our observation wells out there tell us that the groundwater is connected into the Moscow-Pullman area, but it doesn't tell us how well it's connected. And I'm of the belief, and I presented that in the model, that there are much lower values out here than they are up in the Pullman and Moscow area. However, I have to admit, going over, reviewing some of the references that I use, I couldn't find anything more other than circumstantial evidence to guess at those numbers. So I'm going to suggest later in the recommendations, how do we figure that out? That's a very weak link in understanding our system. Most of the numerical models in the past have helped us think about the area, but they essentially haven't been good predictors, and I believe it's because they haven't downgraded this area. What I mean by downgraded is it needs to use lower hydrological parameters than they use from the Pullman and Moscow area. So I would suggest in the future, we might be able to get some numbers by running pump tests up here in Pullman. Now we have observation wells out here to the west. We ran some large pump tests back in 2010, 2011, and But we didn't have any observation wells out there of any significance. Now we've got 3 good observation wells. So I believe if we run tests up here in Pullman, pick up the data out from those observation wells, we can determine a couple things. Is the idea that there is a barrier produced by the folds, the structures, the dikes, and so forth? Is there a real barrier between Pullman and the Union Flat Creek area? Are the numbers lower, higher, or equal? Any future model, numerical model in particular, would need to know those numbers. But looking at it, I couldn't find anything new. The other option is to drill a deep production well, very expensive. I think running the pump test in Pullman would be a lot less expensive. Now, the third area that I picked for a focus on a model, if you recall this slide, I depended on thinking that particularly the Pullman anticline, this anticline shown here going up towards Albion, that anticline on a northwestern dipping block is causing the water to move to the northwest towards Albion. And then the intraflow contacts in Albion are lower than the intraflow contacts across the central part of the basin. The central part of the basin, the Moscow-Pullman basin, the contacts are horizontal, but I believe the structures in this little area around Albion, about a 9 square mile area, where the folds are plunging, meaning that the slope of the fold is increasing and causing the intraflow contacts to drop into the Albion area. So I think we presented that the folds and this sink, I call it up here in Albion, is controlling the way the groundwater is moving and trying to get out of the Moscow-Pullman area out into the west. So we looked at, I decided to relook at this area a little bit and draw some cross sections and do some thinking. There's enough cross section we've already presented to know that this Pullman anticline is real. It's not an interpretation. It's not a figment of geologist imagination. We've drawn several cross sections across there. There is an anticline. It's small, and it does plunge up towards Albion. So let's look at that same area. Here's a different diagram showing these folds. We're going to look at a cross section. This is, by the way, I forgot. This is, those who follow and probably know what this is. This is the generalized structural contour map on the top of the upper Grand Ronde surface. We're going to draw a cross section from up here where the rocks are horizontal or near horizontal. We're going to go from the Pullman DOE well between Moscow and Pullman, about this position, and we're going to draw a line up to what we call the Banner Road well and see what we see. This cross section is not as pretty as some of mine in the past, but I think it can show the same information that I'd like to get across. It's about 6 miles between those two wells. The DOE Pullman observation well is off on the right. The DOE Banner Road well is off on the left. It's about 6 miles between the two areas. And since I had to draw a sort of a squinched cross section, these slopes you see over here between the contacts are a lot steeper than they are in real life, but they help us illustrate what's going on. The first 3 miles, half of the distance towards that Banner Road well, the contact between the various rock units, the salts and the sediments, are near horizontal, and the intraflow zones would therefore be near horizontal. What happens as you approach the sink, as I call it, at the DOE Banner Road well, is that the contacts start to drop, and therefore the intraflow zones, which we know are the key to groundwater movement, drop down towards to the northwest. And these intraflow zones are probably average about 30, 35 feet thick as a general estimate. So here, the slope is going down across the present day or close to the present day water level. I drew a horizontal line on there to represent a water level. When I did this, I used 2240. I think present day we're down to about 2238. But the point is, you can draw a horizontal line, and what you see happening is, of course, it's going to cross these intraflow zones. Here, there's one between the basalt of Lolo, the Vantage sediments, and the uppermost Grand Ronde. One out to closer to the center, the water level would be crossing the intraflow zone and the Mara Ridge flows. The point that I would like to make, and what I think is, let's just look ahead, excuse me, let's look ahead and say we drop the water level 40 feet and look at what would be going on at 2,200 feet. Well, if you drew a water level across at that point, what you'd realize is, of course, you no longer have as much of the interflow zones that have water going into them. Stumbling a little bit here. Let's back up. As you lower that water level, what you are exposing is areas that were once discharge pipes. We know the water moves down the slope of interflow zones, down the dip. So if you were at this point, at the water level, you lower that 40 feet, what you've done, now you have less of the interflow zones that have water running through them. And that means that you have decreased the number of discharge areas as time goes on. So I would suggest that here's a geologic control on water level decline, because if you decrease discharge, you're also decreasing the potential water level decline. Of interest is that this is a geology type diagram put together with my Walmart calculator. And this zone across there, I would estimate to be the zone of where the water level is crossing the intraflow zone. It's about 5,000 feet. I had an engineer calculate the slope. The slope that's illustrated is really only about 1%. Have an engineer calculate out how much distance in this 3 miles would the water level be going across an interflow zone. And he come up with each one of these spots would be about 6,000 feet. So more accurate calculation possibly. You add that together and you realize that there's, out of the 3 miles, there's over 2/3 of it's almost 2 miles is where the water level is going across those intraflow zones. So when you drop it 40 feet, as I was just looking ahead, you're now, you can't say exposed, but you no longer have as many drainage discharge areas as you had before. You might think of it as like a dam. Let's think of the Hoover Dam. Suppose somebody had put a small row, small in circumference, a row of discharge pipes going at an angle. Instead of going horizontal, we're going to run from one corner of the Hoover Dam across the other corner, only it's going to drop. It's going to be at an angle. But what will happen as the water levels drop as they are now in the last decade, as the water level drops, you're going to decrease the discharge because you no longer have as many pipes that are allowing water to flow out of the dam. Well, I think the subsurface in the Pullman area, in Pullman, operates in the same fashion. Another diagram to show the same kind of thing. This is the cross section over 4.5 miles from Pullman down here on the southeast corner of the map on the right, up to the Albion City Well, which is only a couple thousand feet from quartzite basement rocks. And what you see is sort of the same thing. Here's the interflow contacts dropping down the plunge of that fold. Just the cross section is almost right down to the center of the anticline. And what you see is the same thing. You see, since the inner flow contacts are dropping, then you have the water level crossing these interflow zones. And if we would drop it another 40 feet down here to the 2200 level, you would see we now no longer have the same amount of the Rosa flow, no longer have the same amount of interflow zones between the Rosa, the Vantage, and the N2 flow. So if you drop it 40 feet, you're now having these dry discharge areas. This is a particular of interest in this area because we know from our previous lectures that studies by Moxley and studies by the Department of Ecology have shown that along that stretch, it's basically following, if you look on the map, you can almost see, you can see the green, you can see a little bit of the South Fork of the Palouse River. It's been shown by those workers that there is water moving across the cross-section area that I have here from the northeast to the southwest. And this is getting down into the slope of the interflow zones that extend all the way out into the Union Flat Creek area. So there's documented evidence that the water is moving into these contacts at the surface. So once again, I would say if you drop the water level, as you drop the water level, you are sort of increasing the amount of decrease. If that makes any sense, have less, you drop it 40 feet, you have less discharge than you did 40 years before. Let's take a little look and compare that to some of the data that Steve Robuchon has put together. If you're unaware, over the years for PBAC, using the observation wells and other wells, Steve presents every year graphs and charts illustrating the water level changes for the last year. And here's one for the DOE Pullman Test and Observation Well, halfway between Moscow and Pullman. Starts up here back in 2006. We have an elevation of 2,252 feet. We've come up close to the present day, so year off. Right down here we have an elevation of 2,238 feet. So we've dropped that much over the last couple decades. As you notice on the data, the green is the measurements. To me, what I see, and Steve sometimes sees it differently, and other people sometimes see this differently, I see, even though, of course, there are the up and downs from monthly changes, production changes, and so forth, that it's amazing that it seems like a relatively steady decline. It has some ups and downs, and if you measure it real closely, you'll find that the rate of decline has decreased towards the end. But for the most part, I've always been amazed by the steadiness of this. And if you look back to the 1800s, although I think it's been pointed out to me a couple of times, our data down through some of those years is not very good. Well, actually, it's been a similar type of water level decline. And just think of the production changes through those years. Think of the changes in recharge from the mountainous areas during those years. Think of the recharge areas that we potentially covered over with macadam and concrete and so forth. Yet water levels are, to me, fairly consistent. And this led me to think about the fact that water usage and recharge amounts are obviously the keys to understanding water level decline, but there's a third one. And I think the third one is the geologic control that we have that's controlling the amount of decline to a certain extent. Let's look at another diagram that Steve produced. This one's on Pullman well number 3. This graph goes back all the way to 1990. And what's interesting on this What Steve did here was show changes over 3 10-year periods. And we have from 1990 to the year 2000, we have a decline level, an approximate decline level of just over a foot per year. And then we go from 2000 to 2010, and that decline level is averaging is about 0.88 feet per year. Then we go to the next 10 years from 2010, 2020, and now it's down to 0.7 feet per year. Overall, yearly changes are small, probably something like my Walmart calculator estimating something like 0.02 hundredths of a decrease in the amount of water level drop each year. You put it all together, you have to look at these things, as Steve has pointed out to me a couple of times. You got to look at the 5 and 10 year cycles, because you have all these individual. You see the white areas that are drops, and you have some other areas which are highs. You have to even the data out, and you need a 5 or 10 year period to see if the change has been the same. But again, what this tells me is something is causing us now in the last 30 years to have a decrease in the amount of decline. Small, but determinable. Yeah, one possibility is, if you recall, way back in the 1990s, of both the cities and the universities and the public all worked on a heavy conservation program, dropped our production rate, dropped our usage rate. So maybe you didn't see the immediate effects of that. Maybe those conservation methods have helped out in the long run, causing this change in the amount of decrease. It would seem like you should have something more obvious to me up here after we've done all those conservation methods. And that's why I still stick with the fact that there's a potential geologic control on the water level decline. But it is an explanation. As I understand at the present time, we are not pumping as much as we did way back in the 1990s. And another possibility is some hydrologists will tell me that other areas of the world, there are documented areas, as you pump the water levels down, that it causes the recharge to increase. So some people would say that as we have been pumping this area for so long, pumping this lower level aquifer, the lower water aquifer, for so long, that we are causing an increase of recharge around the basin. That's also a possibility. I still think it just seems so systematic that there's another control, and that is the control over in the over in the Pullman area, where we have this cross section, and this area here on this map is between Pullman and Albion, is an area where the discharge is being controlled, and it's slowing down the water movement, and it's also slowing down the amount of water decline. Just something for you to think about in the future. Something that, looking at my model, looking at all the pieces and parts, I call it, is something that I believe is happening, that this area is controlling the discharge. Now, I'm going to stick to that argument. I'm going to make a couple of predictions. You just remember, just a couple cautions. I'm going to assume no major increases in pumpage over in the future. Now, we're obviously got to have some increases. The towns are going to grow. University enrollments might rise. But I'm going to assume no sudden big changes. No, we didn't suddenly start pumping out of water for 6 factories or something like that, or the cities don't grow exponentially. They're also going to assume that no major change in decreases in recharge, in the recharge areas. In other words, there's probably going to be some drought summers. but I'm going to assume that we don't have a 10 or a 20 or 30-year extreme drought situation. So with that in mind, I'm going to use my thinking, use the thinking on the model, and make some simple predictions. And these are something to think about in the future. I think in the next 5 to 10 years, you should see the same small decreases in the rate of decline, because I very much believe in the geologic control. Now, that doesn't mean you just go out there and pump away, and it doesn't matter. It does matter. At some point, and I'll mention this again, at some point, you might stabilize, but you're going to still overpump the amount of recharge. And even though the geologic controls are helping us slow the rate of decline, they're not the solution. Now, I look ahead, oh, by the way, in this 5 to 10 years, I'm 79. So if anybody out there remembers this 10 years from now, and the rate of decline is the same as it is now, or if it doesn't work out and isn't the same, if I'm still alive, call me up and let me know. I'd like to know whether I was right or wrong. Now, the water level decline, if it stays the same, about 0.7 feet per year, people are always asking, well, about 50 years down the road, what's going to happen? Well, if it stays the same, let's say it levels out at 0.7 feet per year. Well, in 50 years, we'll drop about 35 feet, 35.5 feet. So who's that affect? Well, that affects some of the domestic wells if there's not enough depth to the well below where they are pumping. Overall, in terms of the future in terms of the amount of water, we're still way above the saturated aquifer system. We'll probably still have plenty of water for another 150, 200 years after that. But it will affect the wells. The municipal wells are pretty much designed at the present time to be able to accommodate that drop. Now, third, if the rate of decline continues to decrease as it is now, as we've shown on the well from the Pullman well number 3, 50 years from now, somewhere in nearing 50 years, the water levels are going to approach stabilization. In other words, what I think is going to happen is that you're going to continue on with these small decreases. And at some point, the water level is going to approach where it's only dropping an inch or two a year, or maybe even stabilize. If it stabilizes at that point, we'll be able to determine precisely, very closely, be able to predict the amount of recharge into the area. And once again, I would say that may not last. Just because I believe that we will stabilize in 50 years, that may not last if you keep increasing the amount of pumping. There's still a limited amount of water coming in to the basin. I won't be around in 50 years, so I can make this prediction and I use it. It's pretty close. I think it's pretty accurate. Now, from all the work, all the lectures, all the predictions, today we just did some thinking of the model and so forth, make some recommendations. I usually do not like to make the recommendation to the mothers and the fathers of the Moscow-Pullman area. I like to do the science, describe the geology, add in the hydrology, and end at that. But I do have some recommendations that I would like to set forward. Well, one, I know we're doing some important work on alternative mechanisms for adding to our water system, our water amounts. But I think we should still do a little research, take some Pullman pump test. I mentioned that before. I think the Pullman pump test using Pullman number 8 or Pullman number 5, that we could produce some numbers that would be useful and near accurate, good estimates of what the system is like west of Pullman, and find out whether in fact there is a barrier, or maybe there is no barrier. Maybe the groundwater parameters out there are the same. But those numbers that you could find from the Pullman pump test, I believe, would help make a numerical model and might help verify or discredit some of my predictions. That also suggests that the South Fork River from Pullman to Albion not be overlooked. It's like 3 miles. When you head into the meander part of it, it's probably 4 or 5 miles long. Excuse me. That area is receiving water, is definitely getting down onto the top of the Grand Run, and it's flowing out into the Union Flat Creek area. And I believe that's how we are connected. The Moscow Pullman area is connected to the Union Flat Creek area because of that recharge. So I wouldn't say it'd be too expensive studies. Not me. Somebody knows something about recharge along stream channels, revitalizing stream channels. Maybe there's a possibility that you can increase the recharge there. Probably not a huge amount, but the South Fork of the Palouse River flows pretty high for a while in the springtime. A lot of potential recharge there. And particularly look at it so we don't destroy it, that area, from recharge in the future. Then I would suggest we get up onto Moscow Mountain slopes again. We've done a lot of research there, mostly Brooks students at the University of Idaho and Jeff Langman students at the University of Idaho. Those studies were the ones that identified the recharge areas. They and I, both Jeff and Aaron, I believe if I talked to them today, they would agree that the water is getting into, is channelized into a very complex system of channels, interwoven channels. It also, I think, agreed very hard to tell where all those areas are. Brooks has identified some from their studies, but it's haven't come up with an area, a method by which we could just say this area is a good recharge area, this area is a good recharge area. Primarily because there's just not enough data to do a subsurface model where there's channels for that. But I would think, I've been rethinking this, I think a study up along the edges between the Moscow Mountain slopes and up into the trees up towards Moscow Mountain, that area I think has some potential for is recharging, so the areas that are recharging. It's thickly covered with weathered granites and quaternary sediments, but I believe you could find some other areas and only have to do shallow drill holes to verify that there's recharge. And maybe some of those areas can be easily changed to accommodate extra snow melt, extra runoff water. There's a lot of ponds and poor drainages up there. So I think that area should be still looked at as a potential area for increasing our recharge. And my last recommendation, which I've mentioned many times before, whatever we do, we want to keep maintaining those water level measurements for 2 reasons. If we look down the road 30, 40 years, somewhere along the line, you're going to need some new wells or replace some wells or move a well site. Whenever that happens, you'll need to hire consultants. It's not just like the old days where I would drive out to an area or I would ride along with somebody and say, what do you think about here? It's not going to be that way. You're going to have a lot of environmental papers filled out. You're going to have to know what you're going to encounter. And you're going to have to hire a consultant. The first things they ask, consultants will ask is we want to see the water level history. That's a key. That's one reason. The second reason is that those observation wells, those water level measurements, are the early warning system to how the model is working. Did 2 dry summers influence the amount of water decline? Did 2 consecutive years of increasing the pumping affect the water decline? You need to know that. You need to keep track of that. So that's my recommendation. It's something most solid. I would be myself personally, I won't be around, but I would be frustrated if you did not maintain those water level measurements. Well, I'd like to thank you, particularly those who had the perseverance to follow the talks all the way through. and to those that maybe only listen to a talk or two. But in any case, I hope I've increased your knowledge of the Moscow Oman aquifer system, and that allow you to do some more thinking and testing of models that I presented in the future. Thank you again.